Today I'm going to take one completely ordinary SQL query and make it 1,000 times faster. Not 10% faster, not twice as fast, 1000x. And I'm going to do it live, with real measurements at every step, on 1,000,000 rows of data that we'll generate together right now. The tool that makes this possible is the database index. Every backend developer uses them. Most have never watched one work. By the end of this video, you'll be able to read a query plan, spot the queries that are quietly killing your app, and know exactly which index fixes each one. First, we need a victim. I'm using SQLite through Python's built-in SQLite 3 module because it needs zero setup and everything we learn today transfers straight to Postgres and MySQL. Here's the schema. An orders table, like every e-commerce backend on the planet. An ID, a customer ID, a status, a total, and a created at date. And now 1,000,000 fake orders. Random customer IDs up to 50,000, a random status, a random total, and a random date in 2025. A generator expression feeds execute many, which is by far the fastest way to bulk insert from Python. Let's run it. 1,000,000 rows, generated and inserted in about 7 seconds. We now have a 50 megabyte database file sitting on disk and exactly 0 indexes on it, apart from the primary key. Perfect crime scene. Next, a tiny benchmark harness, because I promised you real measurements and honest ones. Here's bench.py. The run function takes a query and does two things. First, it asks the database to explain query plan. That's the database telling us its strategy before touching any data. Second, it runs the query 5 times and keeps the best time, so disk caching noise doesn't fool us. So from now on, one terminal command gives us the plan, the row count, and the best of 5 timing for any query we throw at it. That's our microscope. Let's go find something slow. The most natural query in the world. A customer opens their account page, and we fetch their orders. Select star from orders where customer ID equals 4242. Watch the plan line closely. 14 rows came back in 110 milliseconds. And the plan says it all. Scan orders. Scan means the database read every single one of the 1,000,000 rows, checked the customer ID on each, and kept the 14 that matched. To find 14 rows, it touched 1,000,000. That is the definition of wasted work. Now here's a fun control experiment. Let's look up a single order by its ID instead, 0.0 milliseconds, and the plan says search, using integer primary key. Interesting. We never created an index, yet this is instant. That's because a primary key is an index. The table itself is physically organized around it, which is exactly why ID lookups have always felt free and why nobody notices the problem until they filter on any other column. And it's not just lookups. Here's an analytics-style query, count an average of all paid orders. Same story. Scan orders, 144 milliseconds. Now, maybe you're thinking, 100 milliseconds, who cares? On your laptop, with one user, nobody. On a production server handling 1,000 of these per second, this query is your outage. These milliseconds are where death by 1,000 cuts comes from. Before we fix it, you need to know what an index actually is, because it's simpler than the textbooks make it sound. Think of the table as a giant, unsorted pile of rows. Finding anything means checking everything. That's our scan. An index is a second data structure stored right next to the table. Conceptually, it's a sorted copy of one column, where each entry carries a pointer back to its full row. Sorted is the magic word. In sorted data, you can binary search. Jump to the middle, too big. Jump left, too small. Jump right. 1,000,000 entries takes about 20 jumps. In practice, databases store this as a B tree, a wide, shallow tree where each node holds hundreds of sorted keys. 1,000,000 rows fit in a tree roughly 3 levels deep. So any lookup is, walk 3 nodes, follow the pointer, done. A handful of page reads instead of 1,000,000. That's the entire trick, and it's about 400 years old. It's the index at the back of a book, industrialized. You might wonder, why a tree and not a hash table? Hash lookups are constant time, even faster on paper. but a hash scatters values randomly, which means it can only ever answer exact equality. A B tree keeps values in order, so the same structure accelerates equals, greater than, between, and order by, all at once. Databases picked sorted trees because real queries are full of ranges and sorts. Keep that in mind. We'll exploit it in a minute. Let's cast the spell. Create index. I'm naming it IDX orders customer. On orders, customer ID. One line of SQL. It takes about 2 seconds to build because the database has to read all million values once and sort them into the tree. One-time cost. And now, the exact same query as before. Same table, same million rows, same 14 results. Look at this. 0.1 milliseconds. From 110 to 0.1. That is a genuine 1000x, and I did not touch the query. And see how the plan changed? Scan became search, using index, customer ID equals question mark. Scan versus search. Those two words in a query plan are the difference between a database that touches everything and a database that walks straight to the answer. If you learn one diagnostic skill from this video, it's checking for that word. By the way, who decided to use the index? We didn't tell the query to. That's the query optimizer, a little planner inside every database. For each query, it considers the available strategies. Full scan, this index, that index, estimates the cost of each, and picks the cheapest. That's also why the fix was invisible to the application. Same SQL, same results, new plan. Indexes are pure infrastructure. But the optimizer can only pick from indexes that exist, and it can only use them when your SQL lets it. Which brings us to the ways we sabotage it. But here's where it gets treacherous. Watch how easy it is to turn our beautiful index back off by accident. Same query, but I'll write the condition as customer ID plus 0 equals 4242. Mathematically identical, right? Plus 0 changes nothing. Scan orders, 110 milliseconds. The 1000x speed up, gone. Because the index stores customer ID values, sorted. It knows nothing about customer ID plus 0. The moment you wrap an indexed column in any expression or function, the sorted order stops being useful, and the database falls back to checking every row. And this exact bug ships to production constantly, just wearing better disguises. Lower of email equals some string. Date of created it equals today. Casting a column to compare it with a different type. Every one of those is a silent index killer. The rule is, keep the column naked on its side of the comparison and transform the other side instead. Lowercase the input, pre-compute the date range, fix the parameters type. Same result, index intact. Indexes aren't just for equality. Sorted data is amazing at ranges too. Here's a report query, count the orders from June. Between June 1st and June 30th. No index on created it yet, so, predictably, scan 140 milliseconds. Index on created at, built in about 3 seconds. And now the same range query, for milliseconds. 35 times faster. For a range, the database binary searches to June 1st, then just reads forward, in order, until June 30th. One jump, one contiguous walk. Notice the plan says covering index, by the way. That means the query only needed created at itself, and the index contains those values, so the database never touched the table at all. It answered everything from the index. Hold that idea, it's about to matter. And here's a gift most people don't expect. The 10 newest orders. Order by created at descending, limit 10. Sorting a million rows to grab 10 should be expensive, 0.1 milliseconds. Because the index is the sort. The database just reads the last 10 entries of the tree, backwards. If your query has an order by that matches an index, the sort costs nothing. Feeds, leaderboards, latest 10 anything. This is how they're fast. While we're here, one pattern deserves special attention because it burns everyone eventually. Like queries. Let's count June orders using like 2025-06-%. A prefix pattern on our indexed created at column, and it scans 57 milliseconds, reading the entire index end to end instead of jumping to June. Why? SQLite's like is case-insensitive by default, and a case-insensitive match can't trust a case-sensitive sort order, so the optimizer plays it safe. Postgres has its own version of this trap with locale-aware collations. The between query we wrote earlier expressed the exact same June filter and ran in 4 milliseconds, 13 times faster, because plain comparisons trust the sort order unconditionally. Same question, different phrasing, one order of magnitude. And if the pattern starts with the wildcard, like %-06-%, no database on Earth can index that. A-B tree is sorted by how strings begin. A pattern that starts with anything has no beginning to search for. That's why search boxes that do contains matching over big tables eventually melt, and why full-text search engines exist as a separate technology. Now, our analytics query is still slow. The paid orders one. It filters on status, but also averages the total column. So let's build a composite index, an index on 2 columns at once. Status first, then total. Think of it as sorting by status, and within each status, by total. And the analytics query goes from 144 milliseconds to 24. And look, covering index again. The query needed status for the filter and total for the average. Both live inside this index. The database computed the whole answer, count and average over 200,000 paid orders, without opening the table once. Designing indexes so they cover hot queries is one of the biggest levers in database tuning. But composite indexes come with a famous gotcha, the leftmost-prefix rule. Our index is status, total, in that order. What if I query on total alone? Orders over 499, no status in sight. And look carefully. It says scan using covering index. 95 milliseconds. That word scan is doing the heavy lifting. It read the whole index end to end, a smaller object than the table, so slightly faster, but it could not search, because the entries are sorted by status first. Totals are only sorted within a status, not globally. It's exactly like a phone book sorted by last name, then first name. Finding every Smith is instant. Finding everyone named Ada, regardless of last name, means reading the whole book. So when you design a composite index, the column you always filter on goes first, the ranges and sorts go after. Column order isn't cosmetic. It is the index. So why not just index every column and retire? Because indexes aren't free, and I want to measure the price, not just assert it. We currently have 3 indexes on this table. Here's 20,000 fresh inserts with all 3 in place, about a fifth of a second. Every insert had to update the table, plus all 3 trees. Now I'll drop all 3 indexes and insert the same 20,000 rows again, 0.04 of a second, for to 5 times faster to write. That's the deal you're making. Every index is a tax on every insert, update and delete, paid forever, plus disk space for each extra tree. There's one more concept that decides whether an index pays off. Selectivity. How many rows does a value match? Our customer ID index was spectacular because each customer has about 14 orders in a million. Incredibly selective, the index eliminates 99.99% of the work. Status, on the other hand, has 5 values, so status equals paid matches 200,000 rows. Watch. Even with our covering index, counting the paid orders takes about 9 milliseconds, not 0.1. Still a solid win over 140, but nowhere near the 1000x, because after the jump, the database still has to walk a fifth of the tree. The rule of thumb. High cardinality columns, user IDs, emails, timestamps, foreign keys, make phenomenal indexes. Low cardinality columns, status flags, booleans, country codes, are weak alone and mostly earn their keep as the leading column of a composite index, like ours does for the average query. So the craft is choosing. Index the columns where clauses, joins, and order bys actually use, guided by query plans on real workloads, and skip the rest. A read-heavy dashboard can happily carry many indexes. A write-heavy event log wants almost none. And when a query is slow in production, The workflow is exactly what we did today. Explain it, look for scan, find the missing or broken index, measure again. Let's lock in the whole toolkit. An index is a sorted B-tree copy of your columns, turning million row scans into a few jumps. Query plans tell you the truth. Search means the index worked, scan means it didn't. Expressions on a column silently disable it, so keep columns naked. Composite indexes obey the leftmost prefix rule, and covering indexes answer queries without touching the table at all. And every index taxes your rights, so you choose them with measurements, not vibes. One create index statement took our real query from 110 milliseconds to 0.1. There are very few one-liners in software with that kind of return on investment. The whole lab, the million-row generator and the benchmark harness, is stuff you can retype in 10 minutes and point at your own schema, and I really recommend you do. Explain plans get addictive fast. If you learned something, a like helps the channel enormously, and subscribe for more measured deep dives. Next up, we're mastering regular expressions, live, pattern by pattern. See you there.